Okay, so now before jumping into that, let us look at the quantum computing, and we will take a look at how the quantum computing is basically is able to break the traditional cryptography, as they call it. And that is where the emergence of new cryptography is coming, which is called as a post quantum cryptography. Okay. So, what does a quantum computing brings on the table? See, you guys might be sitting on a desk or a laptop, right now. Imagine a quantum computer of that size, your desk size, and imagine the amount of power that it can pack. That size of quantum computer, your desk size quantum computer, by the way, can pack the power of 1,000 params. We are all aware of params, right? Our supercomputer, the Indian supercomputer. How does it do it? How does this amount of massive computing power is available? See, one of the thing I always tell very, very simply to make explain the quantum computing is earlier we used to basically do the 32-bit. We used to have a 32-bit processor, right? Inside our own laptops and desktops, everybody, right? So we used to have 32-bit processor. Subsequent to that, 64-bit processor came. And we said, my machine is now double powerful. What is my machine? My machine is double powerful. Why is that? Because I can do a 64-bit parallel operations on my machine. I can process those 64 bits, right? So my computing power goes very, very high. In the case of a quantum computing, 64 qubit, okay? 62 qubit means 2 raised to the power, actually 2 raised to the power more, 16 into 10 raised to the power 18 or 2 raised to the power 64. That is the amount of computing power that will be available with a 64 qubit processor. That is there. Now, a question in the room, okay, and you guys can respond by unmuting yourself, probably. Just minute, I am just rushing it ahead a little bit. Okay. Um, what is the largest quantum computer that is available today in the into the world? Anybody, any guesses? Largest amount of quantum computer. The largest quantum computer that is available in the world today is 1,000 qubits. It is getting there already. 2026, IBM has released a quantum computer called as an Osprey, which was the largest one. Okay. But there is a US company, the name is not hitting me yet. What is that US company who is basically saying that quantum annealing computer, it is they are actually do they can actually have the 1,000 logical qubits which you can process. Imagine the amount of computing power that is available, right? Why is this possible? Why is this possible with a quantum computing that is there? See, one easy thing to understand the quantum computing is I am pretty sure you guys have heard or read about it, but just for a completion sake, right? See, in the classical computer, you can process zeros and ones, right? Either a bit can be 0 or 1. In the case of a quantum computing, one bit could be anything. It could be 00, it could be 10, it could be 11, it could be 01. All possible combinations of the bit are available within the quantum computing because of the quantum mechanics that is involved. Now, I'm not going to go into the details of quantum mechanics today, right? But I think this is easier to understand that way. That you have an exponential power of quantum computer which is available at your disposal now to do your parallel computation. Now, using this parallel computation, what can you do? Breaking RSA 2048. See, RSA 2048 is the algorithm which is used in our SSL, right? One of the algorithm which is used in SSL, RSA 201. Very, very beautiful algorithm and very, very simple that it basically works on prime factorization, right? The prime factors that we used to do earlier, right, in our journey. So it works on prime factorization and it is very difficult to find another factor, given one factor, for a number that is there. So based on that, there was an asymmetric key cryptography that was designed by Rivest, Shami, and Adi. Okay, that is what RSA. So the classical computer takes around 300 trillion year if you want to do a brute force. What does it mean? Brute force? That if I have a public key, if I have your public key, right? Public key, private key. Everybody is aware of that, right? So if I have your public key, I can figure out your private key. If you want to do a brute force with a classical computer, it takes around 300 trillion years. How much years? 300 trillion years. In the case of quantum computer, it is few seconds. Okay, guys, it is few seconds. Okay, or even minutes that are there, or even microseconds based on what kind of a quantum computer that is available to you. So, highest level of threat that is available to the digital ecosystem today is the quantum computing, right? And what are these two good fellows doing on my screen? Mr. Shore and Mr. Grover, or Dr. Shore and Dr. Grover. What are they doing on my screen? They are telling you that Dr. Shore basically tells that using his algorithm, you can actually do the prime factorization using a quantum computer very, very fast. Dr. Grover, what is he telling you by sitting on my screen? He is telling you that using his algorithm in the quantum computer, you can actually become, the search can become very, very fast. So what is the use of this search in cryptography? So it is no use in cryptography, but it is useful in breaking the cryptography. When there is a ciphertext, when there is an encrypted text, you can do a lot of search and you can try to figure out a key, right? And using Grover's algorithm, you can reduce the amount of search by the factor of square root, right? So if it takes n queries, then using Grover's algorithm, you can actually do a square root of n queries. Now, who's saying that? Okay. Now, let me basically, okay, I think I missed a couple of slides that are there. Now, but doesn't matter. So that is the threat that is available. So what does it mean? It means that all these things that we have developed, all these things that we have discussed earlier, which is identity, the authentication, the key agreement, the encryption, the electronic signature, everything is at threat by the quantum computer based on the algorithms that are there. Now, but this is not the end of the world, guys. Okay, not the end of the world. We are still there as far as the post quantum cryptography is concerned. So, post quantum cryptography is the field, okay, where you employ a cryptographic techniques that are secure against quantum computing attacks as well. Yes, that is called as a post quantum cryptography. Now, there are 6 areas. I don't know whether I'll be able to recollect all the 6 areas of cryptography which are quantum resistant, but there is a lattice based cryptography, there is a code based cryptography, there is a hash based cryptography. I think there is isogeny based cryptography, and then there is a theoretical information theoretical secrecy based cryptography, right? So there are 6 areas in which the research is going on right now in finding out a right cryptographic algorithm which can be replaced with the existing pre-quantum algorithm like an SSL, right? And bring out a stronger SSL part of it there, right? So that is what is called as a post-quantum cryptography. So this is an alternative that is available. Now, what is the work that is going on here? I think all of us would be familiar with NIST, right? National Institute of Standards and Technology, which is based out of US, right? So NIST has standardized certain algorithms in the space of lattice-based cryptography, saying that you can use that safely till such a point of time somebody breaks it, right? So cryptography journeys are like that only. Till somebody breaks it, it is secure. Till that point of time, nobody proves that it is not broken, right? You basically keep on using it. So there are 3 algorithms which has been selected by the NIST, and we are doing our own bet in India to create our own cryptographic algorithms as well, right? Which can be used by our national critical installations or our defense folks so that we don't have to rely on the foreign standards, right? So we are working very, very closely with the government on top of it. Our national quantum mission is working on that, right? Already to come out with our own standards. So now this is one thing, which is a post quantum cryptography. Do remember that. We spoke about cryptography. We said then what is the vulnerabilities that is there. And then now we are speaking about post-quantum cryptography. Okay. Now let us move ahead. Cyber physical systems. What does cyber physical system means? Okay, so now in the domain of quantum, again, there is one more important. I'm again now focusing on a post-quantum. Okay, there are cyber physical systems that are available in the pre-quantum era, right? You have chips or you have firmware where you can ensure basically the security of your physical systems as well, the cyber physical systems that are there. IoT devices is your cyber physical, right? How do you ensure the security of your IoT devices? It goes into cyber physical systems that are there. Now, there are cyber physical systems in the cyber security which are available for a post quantum cryptography as well or post quantum resistant. So, one of the important thing, guys, to understand here is see, when you do the cryptography, the most important element in the cryptography is what? What is the most important element in the cryptography? It is the key, right? If somebody has an access to my key, right, that's about it. He can become me. You guys might have heard about lot of fraud that have happened in the cryptocurrency where people have stolen cryptocurrency, right? We are talking about cryptocurrency, um, bitcoins and solanas and all of that. So people have stolen the private key, and that's about it. Once the private key is gone, all your money is gone, right? That is the importance of key. Now, when we sign something, when we do some of the cryptography, if somebody figures out a key, all gone. Why I'm speaking about all of that when we are talking about cyber physical systems? Importance is the generation of the key. How do you generate a key? That becomes important. That means your key has to be really, really secret and random. What is the most important thing? Secret and random. Okay. Now, how do you ensure a randomness in the physical world, in the computing world? Because in the computing world, everything is deterministic, right? Everything is deterministic. Your algorithm, your logic gates, everything is deterministic. So how do you ensure a randomness? So that is where the quantum also comes to the help as well, to the cybersecurity by something called as a QRNG. What is it? QRNG, quantum random number generation. So you use a quantum mechanics, you use a quantum noise to create enough randomness to achieve basically a true randomness. And then using that, you actually um, build a key that is there. So this is first cybers. I'm just giving few examples to you just to make you familiarize in this domain, saying there are cyber physical systems which is where the work is going on. There is second one, quantum resistant cryptography we spoke about, secure remote sensing and surveillance systems. See, this is another area where the quantum computing basically helps. So see, because quantum actually works at a very micro level. When I say quantum, these are all quantum particles. Now, what are quantum particles? Quantum particles are atoms, photons, are not atoms, the protons, neutrons, and electrons, right? These are subatomic particles. Subatomic particles are called as a quantum particle. Now, if you are able to work with this particle, you can even detect a very, very small, a tiny change that is happening within the environment that is there. That is where there is a work that is going on into remote sensing. If you want to sense sitting in your home, what is happening somewhere else or on the border, you can use that remote sensing in the surveillance system as well, right? You can use it for side channel attacks as well. I will reserve this question. People may ask a question, people may ask this question at a later point of time saying, Nilesh, tell me about the side channel attack. What does it mean? And how does the quantum protect against the side channel attack? And then there is a last thing, not the last, one of the other thing is basically the QKD. What is the QKD stands for? Quantum key distribution for ultra secure communication of your keys. When you want to transfer the key, let us say, okay, now let's take an example saying your institute and Army Institute of Technology has to communicate very, very securely their keys to each other. What are the ways to do that? One is you transfer physically. If it is a symmetric key, you transfer physically. You send somebody there and you say, okay, take this key, sir, now, Sagar, sir, and put it there, put it there. And similarly, the key is available. The second way for doing that is the quantum key distribution. What does that mean? You actually lay an optical fiber line. At the end of optical fiber line, you have the quantum devices at both of the ends. What is the advantage of this? The advantage is when you transmit a key from one device to another device, when you transmit a key from one device to another device, if the attacker even looks at the key changes. The key changes because of the quantum mechanics. Even if the attacker looks at the key changes, right? So that is the importance of the cyber physical system. So what are the ways to protect ourselves from the quantum computer? The protect is post-quantum cryptography, and then there are cyber physical systems that you can employ for protecting yourself from various attacks from the cyber. Okay. Now, let me just take a pause here to see if you guys have any questions. Otherwise, let's now go to the, so far what we have spoken about, we have spoken primarily around cryptography. What is our today's theme? Our today's theme was cryptography and digital identity. So what we are going to speak right now, we are going to speak about digital identity and its models. Yes.
कारण
Yeah.
आता सोडलं की ते असे उडतील केस. मग हे घरी करायचं असतं ना आपण.
Okay, anybody has any questions, or I'll move to the digital identity and its models. Okay.
No, sir, we
Or
can continue.
we will, yeah, okay. Or we will wait for the end as well. So is this a right statement? This is the right statement. Everything is driven by identity. Okay. Everything is driven by identity. Why do I say that? Okay. Sorry, I think I got muted. I'm audible there, right?
Yeah,
Yes.
yeah, you are.
Okay, perfect. So when I say everything is driven by identity, so for beginning of any communication, you need to establish an identity and authentication. Otherwise, communication has no meaning. That is why everything is driven by an identity. Now, what does the identity means? Okay, if you look at the identity for an entity, it is an ability to prove that it is who it is claiming to be. It is an essential requirement for accessing the services needed for its survival. Of course, right? Without, if you are not able to prove your identity, you cannot get any services. You cannot go to even the government saying, okay, give me these services and all that. You cannot go to even your office and say, boss, I'm he or I'm she, right? And all of that. It is extremely critical to establish a digital trust, right? And association with a physical world entity. So Nilesh in the digital world and Nilesh in the physical world, there is a association. I'm carrying my mobile phone, I carry my identity inside there, I'm carrying my Aadhaar ID or I'm Aadhaar on that. So that association becomes important. Okay. But okay, let me come back to this slide little later on, why the identity management is complex. Now let us look at basically an identity model itself and the evolution of an identity models. Very, very interesting. Okay. We are all familiar with the LDAP or DB based identity models, right? When we say that, boss, I'm maintaining my student's identity inside my college premise. What does it mean? Your ERP system is having all of your student identities, professor identities, all of that. Typically, you are maintaining that within an LDAP, right? So this is the oldest model, an identifier based model where you say that, okay, I will give you an EDID and this is the number and the password, and this is how you prove your identity to me every time you want to access and service. Okay. So what we are going to discuss is we are also going to discuss about the limitations of each of the systems that are there. The second is the cryptographic model. Cryptographic model, very, very clear. Symmetric cryptography, public key cryptography, identity-based cryptography. Okay. Now, why do I say cryptography is also an identity model? Because the possession of the key also proves the point that it is indeed who you are, right? By possessing my private key, I can prove that I am Nilesh. Somebody sends me his data by signing using the public key, and I can verify that, right, using my private key, and vice versa as well, right? Both of the operations are possible. Similarly, is the symmetric key. And then there is another field, which is probably, I don't think it is a new field, but less people have heard about this. This is an identity based cryptography. The Shamir guy, actually came out with a protocol of the cryptography, of the identity-based cryptography. And lastly, but not a least, it is a blockchain model, right? So there are now blockchain models of an identity also that are there present in the world. Some of you would have heard about WorldCoin. Any of you have heard about WorldCoin saying if you sign up, give an iris? There was a movement that was going on in India as well, right? If you give your iris, we will get your identity registered onto the blockchain, and we will give you 10 coins, 10 world coins, or 20 or 100 world coins. I don't remember at that point of time. So what does it mean? What does each of this model means for us, right? So three models: attribute based, cryptographic model, and a blockchain based model. And why this evolution has happened. Okay. So first we started with an attribute based model where what we said is we will keep all of our data, identity data, within the database. The problem with that is, if let us say there is a system administrator or a database administrator or somebody who has an access to the system, he or she can compromise your identity, right? That is the problem with an LDAP. Second is, there is no provable association. Remember the keyword. There is no provable association between who you are as a physical entity and what is there inside a database. Provable association is missing. Okay. In the cryptographic model, the most beautiful model that has evolved was a digital certificate model. See, if I have a digital certificate with me, my own, by doing a KYC with a CA, right, and I can prove my identity provably to the other party, to the bank, to the government, to even peer-to-peer communication and all of that. So that is the cryptographic model. What was the problem with that? The problem with the cryptographic model is because it is so cumbersome to distribute a digital certificates and to manage the life cycle of that certificates. Okay, this model has not got adopted as in the large scale for a retail population. Okay, it has not got adopted for a retail population. You and me do not have digital certificate typically. I have because I am owner of a company and all of that, but most of us do not have that. And the last model is the blockchain model. See, blockchain was a reaction to system. When we speak about bitcoins and all of that, it was a reaction to system, right? That who are you to come in between when two parties wants to transact with each other? Why do banks should come into the picture? I want to transfer the money directly without bank to the other party. That is why blockchain came into the picture. Similarly, in the identity itself, people started saying, why should somebody come, or why should government give you an identity? Why should they give you a social security number? Why should they give you a Aadhaar number? We will create our own identity into the blockchain, right? And we will transact using that. Okay. Beautiful model. The advantage of this model is that it is a inherently privacy preserving model, because your data is not with anybody, right? It is there into the blockchain, and it is tamper proof, of course, unless the collision happens between multiple parties that are there, right? But what is the problem? The government cannot control them. The governance becomes a problem. So regulated entity and adoption becomes a challenge, right? Again, the threats of quantum computing are there. So this is the evolution of identity models. Now let me tell you one more problem. See, we have been discussing about problems and problems, but we have been, when you think about a problem, also the solution also arrives in time. Now, let me just go back. So we spoke about all of this identity. Another one important thing is, see, identity is the most notorious thing in the cyber security world. If you are able to fix your identities and access control, 99.7 or 9% problem goes away. Now, why? Why identities are a problem? See, this diagram tells you all about it, why it is a problem. See, these are all the identity technologies which are there in the world, right? So you have identities of humans, machine, application, APIs, and by the way, all of these guys has to communicate with each other, right? So you have identities, you have assurance, KYC, data sharing, onboarding, attribute assurance. This is an assurance technologies. You have category silos as well. So when you access your google.com, you use a federated identity. When you access your ERP, you use an ADID, right? When you actually access, let's say LinkedIn, there you have something different altogether. Similarly, when you go to any of the enterprise, there are category silos as well, right? You have employees. So you have employee identity and access management. For customer, you have customer identity and access management. For consumer, you have federated identity and authentication. For administrator, we have PIM and PAM solution, and the list actually goes on. So does the authentication solution. And then there are access silos, and then there are privacy silos as well. That is why identity becomes extremely difficult. The management of an identity, because all of these guys, all of things has to interoperate with each other. That's why the complexity increases in the world, right? And that is one of the trend that is going on, saying how can we actually bring all this together into a directory service, into a fabric kind of a thing where all of these identities we are able to manage within one piece that is there. So this is one of the problems that are there. Okay. Now let us look at another thing. So how do we solve this problem now? We solve this problem by looking at an identity into a physical world. See, how does the identity in the physical world looks like? In the physical world identity, when you ask Nilesh, what are you? Who are you? I basically tell you about my uniqueness. Saying I'm Nilesh, I'm a CEO of 42 Labs, I have home here, I have one kid, and the list actually goes on. So it is an intrinsic uniqueness. And second, it is also based on the behavior. So now, because of this, what happens is there are very beautiful properties that have comes to the physical world because my identity is always changing. It is always absorbing something from the environment and it is changing always. And then I'm using myself to participate into the physical world, right? So that's the identity into the physical world. Third thing is my identity is very, very tamper proof in the physical world. Physical world identity we are talking about. Why? Because my past is immutable. When I say I was a CEO I was actually a co-founder of a Unikian, I was part of Infosys, I basically talked here, we went there and all of that. Those is all history. History you cannot go and modify. However, in the current identity systems, you can go and modify anything that is there. That's why those are tamper proof. Okay. And future depends on only on the present. Whatever I do right now decides my future, right? So these are certain identity. So what we are going to do, guys, right now is what are we doing? You might be saying that, okay, why are we discussing about all of this? What we are trying to do right now is based on the problems that we have seen, we are trying to basically evolve a new kind of an identity model, okay, which is tamper proof, dynamic, privacy preserving as well, right? And completely, and you can actually deliver that to anybody and everybody. Okay. So these are certain identity axioms that are there. Every identity, whether living or non-living, needs an identity. Every entity. We discussed about that. API, IoT, devices, humans, even enterprises. Where your colleges needs an identity, right? You are actually your college transacts with the bank. It is not the individual. So every entity needs an identity. If identity does not interact, it does not exist in the digital world, right? If it does not have a footprint, it does not exist. Defined by events, attributes and credentials are a result of digital interaction. What does it mean? Attribute and credentials are result of digital interaction. What does it mean? It means that if I, let us say, complete my college degree, that is a digital interaction that I did, and based on that, I obtain certain credentials and attributes, right? Identity is immutable since past is immutable. Funny thing to say in the digital world, but yes, we will attempt to do that. Identity is dynamic since every interaction changes identity. Uniqueness increases over the period of time. So even if you have two twins in the physical world, over the period of time, the uniqueness increase, right? Because they go through different kind of an experiences inside their life, right? They might do different things inside that. Identity is always owned by the entity to which it belongs. See, one of the important thing, and a wake up call. Okay, a wake up call. If your Aadhaar gets compromised, what will happen to you? And okay, so you will say, Nilesh, my Aadhaar gets compromised, something funny will happen. I'll say, yes, something funny will happen. But who is controlling your Aadhaar security? You say, boss, government is controlling. Oh, that's the problem. So what happens if, let's say, there is a leak, okay, in the government? Anyway, I'll not answer that question. So now these are the problems that are there. Now let us look at the IAM identity model. Okay, what we have come out with. Now, this is the model that we are proposing that is there, which is IAM identity model, which is basically all of these things that we have spoke about, which is unique, namely uniqueness, dynamism, tamper-proof, past independent, attribute and event provable association. So what we have done is, instead of looking at an identity as a static identifier, we said that why don't we basically come out with a model which is a tamper-proof chain of event over a time dimension. A tamper-proof chain of events over a time dimension. Okay, so whenever identity interacts with the digital system, the event goes inside. So that means as soon as the event goes inside, your next identity changes, your next identity changes, your next identity changes. Because of the cryptographic primitives, we make it tamper proof. So there is a true randomness as well, a true uniqueness as well inside this, because you are actually evolving an identity over the period of time. Okay, so that is the ordered set. Though this is how it looks like from the identity perspective. You have a time dimension, and then you can attach any of the attributes, all of that together. Okay. Now, this is not only available for humans, you can make it available to users, applications, and even devices. That means you can create a single cryptographic object out of all of this and create an identity fabric to deliver an identity to everything and everybody to actually achieve the holy grail of cybersecurity, right? And then using this identity, now let us talk about the cryptography, which we spoke about, right? What we spoke about: identity and authentication, encryption, verification, data integrity, non-repudiation. Of course, we have not spoken about the last part of it. So that is where we have actually built out a platform called as a Pi control platform, which is based out of post-quantum cryptography. So this is our own inventions, which we have secured patents in India as well as the US. I'm not going to spend a lot of time on this today because, and if there is an interest, you can always reach out to me on top of it, right? So that is all, folks, right now. So from the summary perspective, here is the summary. We started with basically importance of cryptography, right? Then we looked at what are the cryptographic primitives that are needed for securely operating in the digital world. Then we looked at the problems of cryptography. What are the typical problems that are there? Then we looked at quantum computing, what basically it brings to the table as far as quantum computing is concerned, right? We looked at that. Then we looked at post-quantum cryptography. We also looked at cyber physical systems, right, which can help you basically make yourself quantum safe. Subsequent to that, we looked at identity models, right? The three models that we spoke about: attribute based, which is an LDAP based, the cryptographic model, and the third model was the self-sovereign model based on the blockchain. And we looked at the problems of that. And then lastly, then we arrived at an ideal model, how the ideal identity model should look like, which you can deliver an identity to everything and everybody, right? And you can basically use that identity to participate in the digital world so that you can actually make the things not only secure but trustworthy but also private, right? And lastly, we looked at our platform that the 42 Labs is building, and that's where we got it. So let me now basically stop here and I'm open to questions. Thank you. So Gopinath ji was correct. It was a 362. I believe it was a 364, believe. And there is a company in the US who's actually building 1,000 qubit of a quantum computer right now, based on the quantum annealing technology. Right. So thank you. Good attempt, Gopinath ji. Questions?
Thank you so much, sir. Good evening, Nilesh sir.
Good evening, Gita ji.
We are always glad to have you for our sessions. I request participants, if you have any question, please unmute yourself and ask questions.
Yes, Gopinath ji. Go ahead.
Your model is physics-based, quantum principle-based model or empirical-based? It combines both. Can you?
So see, it is not quantum based, the model. Okay. It is basically, although it uses a physical concept. Probably you may have heard about Markov chain, right? In the
Yeah.
physics, there is a concept of a Markov chain. So we actually brought that concept into from physics to the digital world. Again, nothing to related to compute, the quantum computing. There was a so they see the Shamir actually came out with a protocol called as an identity-based encryption scheme in 1980s. One of the beauties of protocol is that you can give it basically any publicly known string about you, and it will basically create a private key and public key based on the key pair based on that, and then you can participate. What's the beauty about it? You can actually have the provable association between that. The limitation was that you needed to have a trusted third party do the key orchestration. We removed that and we added more things to that. So you can add attributes, events, and all of that. So it is an identity-based encryption scheme, which is an enhanced version that we have designed on top of it.
Thank you.
But a good question. Thank you, Gopinath ji. Any other questions? Okay, then Sita ma'am, should I take a leave?
Uh, Thank you so much once again, sir.
Thank
It's
you.
our honor to
Thank
have
you.
you. In spite of your schedule, you find out time for us. Thank you so much
Thank
for
you.
your time.
Thank you. Have a great day
Thank you.
ahead, everybody. Bye bye.
Sure, sir.
Yeah, participants, we are talking with the second speaker. So in 5 to 10 minutes, we will again restart the second session. Okay? We can take a quick break of 5 minutes, then we will come back again. Good evening, participants. The next speaker is joining in 2 minutes, so all are requested to be there. As she is joining from USA, she's taking 1 or 2 minutes time, and then we will begin with the next session. Good evening, ma'am. Can you hear me?
Here, yes, good evening. I can hear you.
We are unable to hear you, ma'am.
Okay, let me try. Am I audible now?
Yes, ma'am, you are audible.
Okay, great.
Yeah, good evening, ma'am. Can you hear me?
Yeah, good evening. I can hear you. Yes.
Yeah, great. We can hear you. Dr. Sita will introduce you first, and then you can take the charge, ma'am.
Meanwhile, I request ma'am to please share your PPT so that we'll acknowledge whether it visible at our side or not.
Okay, let me do that.
Good evening, all at second session of the day. Today we have among us Dr. Aarti Dikshit. Welcome, ma'am. Dr. Aarti Dikshit, ma'am, received a PhD degree in computer engineering from Wayne State University, Detroit, USA. She has completed the certificate in scientific computing program from same Wayne University. She is an alumnus of IIT Bombay and University of Pune with Computer Science and Engineering MTech and BE. Her professional experience involved a role as a senior scientist, applied research associate, INCI Raleigh, USA, teaching associate professor, electrical and computer engineering department, North Carolina University. She has been associated with Defense Institute of Advanced Technology, Pune, and Savitribai Phule Pune University. She has been a member of Board of Studies and Research Recommendation Committees with reputed institutes and universities. Her area of interest are AI and security analytics, cybersecurity, cyber physical systems, and education technology. She is ACM senior member and chairperson, Regional Activities Committee, ACM W, which is ACM Council on Women in Computing, Global Leadership Team supporting and advocating full engagement of women in computing. She was chairperson of ACMW India from 2017 to 19. She has been instrumental in proposing and coordinating 3-week residential ACM India Summer School for women on information security and forensics. She has received many prestigious awards like 2019 Outstanding Contribution to ACM Award for contributing to growth and diversity of ACM programs in India, especially for ACMW. I request ma'am to please start with the session. Over to you, ma'am.
Yeah, thank you, Yadamar. It's kind of, I'm not able to see or sense the crowd, but a heartfelt namaskar to all of you. It is I'm thankful to the team of AIT to give me an opportunity to come and talk to you about my experiences and share my thoughts on innovations on national security. That is great. I am assuming you guys are able to listen to me. Do you expect me to start video also, or that is not needed? I mean, I'm open to that. Okay. So let me kind of start with my presentation. So I got an invitation from Dr. Rane saying that, ma'am, can you come and contribute something for this FDP that is being scheduled on the theme of defense dynamics and space exploration and trying to bridging the future. And also he gave me some heads up saying that we would have faculty members coming from all different streams of engineering, maybe computer engineering, mechanical engineering, electronics, and so on. So I would try my best to kind of put my thoughts in front of you for different innovations in technology in different areas and how market is kind of taking up. So what I thought is I would kind of start a bit with my little bit experience or my projects, some projects that I have done, kind of quick introduction to that, and then move on to the different industry experts who have to say or who have a great say on what technologies would matter for us in all coming years. Okay, so yeah. So I would like to start kind of with my PhD thesis, the problem that I had worked while I was doing my PhD at Wayne State University. Let me give you a kind of quick background on that. So was working with a team of scientists and innovators in Tank Automotive Division of US Army. This actually is a lab similar to the defense DRDO labs that we have in India, all 50 different labs that we have in India. And they were trying to work on starting a new unit called as Unmanned Ground Vehicles Reliability or Unmanned Ground Vehicles Group. And they were trying to solve some problems. Like they had a problem, or the problem statement was, we have this personnel involved in moving from one place to other place, especially during the Iraq war. And we face a lot of human casualties in this whole process. So how can we kind of use unmanned ground vehicles to find out underground explosives and save lives in the process of maintaining security and surveillance at certain designated places of interest. So also the second perspective of this problem was to kind of understand or take into account the huge losses that are incurred because of unexpected problems surrounding in the nature, as you see some pictures out here. And how can we save, or how can we protect the unmanned ground vehicles, or how can we protect these expensive tanks from this kind of situations as we see on the screen. So the problem was, how can we find out reliability of unmanned ground vehicles network? Now, why I'm saying network here is we have deployed a couple of unmanned ground vehicles on the field, and we are expecting movement of these vehicles for n number of reasons, right? And before starting the movement of these vehicles, can we have some rough idea on what is the probability of success of movements of these kind of movements? Whether we really should move a vehicle from point A to point B, or via certain route, or we should take care, or we should stop for some time, and so on. So yeah, so was there a question or something from somebody here?
No, ma'am, it was not. Yeah.
Okay, okay, yeah. So yeah, I just forgot to mention that feel free to interrupt me, stop me for any questions. I know it's kind of, we are all in this post-COVID fatigue of webinars and online discussions and sessions. So would be nice to see if you can feel free to interrupt me wherever you want for any questions and so on.
Sure. Yeah.
So yeah, the idea was here to kind of take into account. Yeah, so definition comes here that what is reliability of unmanned ground vehicles network. So here we define that as a probability that a component, part, or equipment or system will satisfactorily perform its intended function under given circumstances, like environmental conditions or limitations of operating time, frequency, thoroughness of maintenance for a specific period of time, and so on. So can we come up with some solution for that? So here is what was the solution that was proposed. That why don't we take help of soft computing approach to define reliability of unmanned ground vehicles? Soft computing using AI techniques aligned with I would say core electrical engineering methodologies using VLSI design and so on. And how can we really come up with a solution for that? So what we propose here is that we have a network of, say, unmanned ground vehicles, as you see on the right here. And we define this as a graph with N and B, where B is an ordered pair, N is the set of stations or nodes, as you see here, and B is set of paths between different stations that we see here. So obviously here the B, that is set of paths, is an ordered pair of nodes N that we see here. So reliability, as we said, saw earlier, is probability of success between two nodes connected by n number of branches. Say, for example, I want to move a vehicle from point or station 1 to station 4. What is the probability of success? And that is what we are really keen to understand. Or we have a dynamic network and we want to find out probability of success of, say, something moving from 1 to 4, something from 2 to 3, something from 3 to 4, 3 to 1, or something like that. So if you want to have if we have a dynamic network of this kind, what is the probability of success to kind of achieve this kind of strategy is what we are really interested in kind of figuring out. So in this proposed methodology, what terms I would be using is terminal reliability. That is, terminal reliability is reliability of reaching from one point, one station, which is called as source, to the other station, which is called as destination. So what is reliability of that? And the system reliability or the network reliability or the global reliability or overall reliability, these all terms mean we have an extremely dynamic network which is kind of reconfiguring and changing, and which is we are expecting that it is not centralized or and hybrid centralized where human control is involved. How can we have this decentralized network operating successfully? So this is what we are trying to solve. So let me kind of give you a brief mathematical background here. I'm not going to go into details because that is not the aim of the talk today. So say we have network in series or parallel or series parallel or non-series parallel, which is a small chunk of a network. So obviously big network will be a superset of all these kind of different combinations that we see here. So terminal reliability is the product of probabilities of the branch reliabilities here, and so on. So these are different mathematical expressions which represent the basic method of finding reliability, terminal reliability basically of between two nodes in a graph. So there is a modification here. You take into account what is the reliability of node, because node also can have some reliability, right? So taking into account the infrastructure of elements that are involved at the node level. So there are different expressions for that, as you see in the second column here, and so on. So the crux of this slide is that we are kind of defining the basic method of finding reliability, right? So moving forward, basic method may not serve purpose, may become a nightmare if we have a huge network. So we have some different methods used and proposed using the FNM method or the basic algorithm that I showed on the previous slide, or spanning tree algorithms or BDD algorithms and so on. So different algorithms kind of were proposed and experimented and evaluated for this network, which is kind of changing very dynamically. So path method was used, cut set method was used, and BDD non-overlap method was used here for finding out the reliability. And we find out the MHOP and MHOP reliability with nodes and without nodes. MHOP here, yeah, basically MHTR is multiple hop terminal reliability. Multiple hops, like if I want to reach from the source to destination, I can just have 1, 2, 3 hops and reach here, or I may take multiple hops here. So for different hops, what is the best terminal reliability that we can get? If we try to, can we have it in one hop? Obviously, no, we cannot, right? To reach from source to destination, we need at least 3 hops, right, to reach to the destination. So, and for different hops, what is a possible terminal reliability and so on. So this kind of setup was built to understand what happens. And this, if we happen to go for hybrid, that is human is involved, human can kind of sit and see what is the possibility if I go with one hop, 2 hops, 3 hops, and so on. And different algorithms can be used to see what is the probability of success of having this kind of network setup and movement from point A to point B. So this is terminal reliability in general, using the basic methods. But then when we take into account the situation of vehicles and taking, it's not possible to really have very clear values of the factors or constraints that are going to impact or that are going to decide what is the reliability of moving from A to B, because there are multiple factors that affect this movement, right? Similarly, the station, there are certain set of factors that affect the strength or the reliability of a vehicle sitting at point A, for example. So a fuzzy approach was kind of taken into account and proposed fuzzy node reliabilities, fuzzy branch reliabilities, the fuzzy terminal system reliabilities, and so on. Let me give you a quick kind of glimpse on what can be possible, what are different factors that can be incorporated or are incorporated for fuzzy node reliability. So when we're talking about a node, when we're talking about a station or a vehicle sitting on the station, say factors like signal strength, EMC, electromagnetic compatibility, that is, are the signals from one equipment interfering with the signals of another equipment and so on, and vehicle mobility and so on. So these kind of constraints are taken into account and they help us to evaluate the reliability of a node as we see here on the network, right? And similarly, factors for branch also are taken into account. So let me go a little bit deeper in signal strength, for example. So signal strength, say, can be defined in the range of, these are the 4 possible values for that. And these are different ranges for lower, medium, higher, and very high values. And we develop a fuzzy node reliability model here. And that is used for different labels, different labels four factors are used here, and these are the membership function parameters for them. So similarly, we can kind of come up with a fuzzy node reliability value, take into account different factors that we have, and have fuzzy node reliability value defined in the range with these labels. So we have a range with 8 different values. So these are, say, different rules that are proposed here to take into account different constraints that we have, and we can kind of come up with a conclusive value for the node reliability as we see here. So reliability can be defined in these different categories as we see. Yeah, so just a quick glimpse of surface view and the rule viewers in MATLAB for that. Same thing for fuzzy branch reliability. So for branch, say for example, we take into account the constraints like weather, obstacles, terrain, distance, support, and so on, and try to kind of define the relationship of branch reliability with this. For example, if weather is, branch reliability will be proportional to the weather. If weather is good, we are doing good. If weather is bad, branch reliability will be a little bit lower, and so on. So different constraints are taken into account, and we set up, or we try to find out the branch reliability as well using the fuzzy model. And an example or a test was done on a robotic vehicle. For example, as I said here, we can suitable terrain gives higher or better fuzzy branch reliability, right? So an experiment was done with a terrain. Say we run this robotic vehicle on different terrains, ranging from asphalt parking lot to gravel dirt road, baseball outfield, infield, or parade ground, and so on. Say plowed field and soybean field. So obviously the speed of this vehicle is going to reduce, as you see here, from the asphalt parking lot to the soybean field where we have completely agricultural land and so on. And this was kind of experimented and evaluated on using the fuzzy model. So let me kind of give you a quick bird's eye view on what was done here. So what you do is we determine the reliabilities of node and branches and decide whether, depending on number of nodes in the graph, whether we really can go for actual method of evaluation of reliability, or we have to use approximate method, because it can be expensive. The complexity of this can be really bad if we have huge number of nodes. So approximation would make more sense in that scenario and incorporate. So once we evaluate the fuzzy branch reliabilities and node reliabilities, whether we take into account the node reliabilities, depending on that, we use the respective algorithm. And depending on number of nodes, we use either basic system or spanning tree algorithm for calculating system reliability. So this is how the flow kind of goes. So this is a bird's eye view. What we did was we identify inputs and outputs. We come up with a soft computing model for that. And we generate the unmanned ground vehicle network model and try to use the reliability algorithm software, select the best one fitting according to the different constraints and characteristics of the network that we have. And these are the different methods that can be used. So one step forward, what was done was, if you take into account these networks, it is at times extremely difficult to have hybrid model where we have the command and control center somewhere and human is involved in moving these vehicles. So a thought was kind of put that why don't we have this sitting on the hardware in the vehicles that we have moving around. So FPGA implementation of that was done with the thought that, that can give a lot of flexibility to experiment with the rules that we have developed for this model. And once that was kind of verified, a VLSI chip was designed to kind of implement that, so that this chip can be sitting on the network, on the vehicles that we have, the tanks that we have, and so that these tanks can talk to each other even without human intervention. So this was kind of the broad solution for that problem that we started with, right? The problem was obviously kind of, we have this network, and can we really solve a problem where we want to find out what is the probability of success of setting up a convoy of vehicles and having collaboration and coordination between these vehicles, and kind of coordinating their movements also in that process. Okay. So the other problem that I had an opportunity to work was on the non-destructive techniques for metal plates. This was actually also associated or had links with the problem that we had defined, that these tanks, they get hit by something, right? And some cracks are developed on the body of this metal plates. So now, can we really find out what was the source of impact? Whether we can find out whether there is a crack already there, first problem. And second problem is that what if there is a crack, then what can be possibly the source of impact? So this was a problem that was kind of to be solved and to be linked with the network here, so that this can be incorporated in either fuzzy node reliability or the branch reliability, right? So of course, that would be a component within the fuzzy node reliability, because it's impacting the vehicle that we are taking into account. So, excuse me. Yeah. So for experimentation, what was done was two sensor arrangement of ceramic plates was kind of taken into account, and we had hammers of different metallic bodies that can really impact the ceramic plate. Ceramic plate can be considered as a tank body here, for example, and the hammers are possible objects that can really hit the ceramic plate, that is a tank. And sensor A and B were used to kind of grab the information about this impact of the hit on the ceramic plate here. So what was done, as I said, we had two sensor arrangements, and we hit the surface with a defined source. Had taken just two sources right now, the steel and delrin, and the data acquisition system acquires waveforms generated by impact here, and the sensors we save waveforms of using the sensor A and sensor B data files, and we process on these different parameters, as you see on the screen here, the RMS values, mean, median, mode, peak values, and FFT values, and so on. So basically, for us, for naive users, let us assume that we extract some information from these sensors, right? And now we have to kind of decide the ranges for different labels that we are using for the system here, and we generate the rule base, define the fuzzy inference system, and once that is done, verify the results and go for the FPGA implementation again. Now, why are we going for this FPGA implementation? Because we want to have this in decentralized kind of network. So we are trying to have this tank independent of human intervention, independent of connectivity with the outside world, because they can be in the wilderness, somewhere in really rough terrain, somewhere in the regions where connectivity might be an issue with the command and control center. So again, the fuzzy impact source identification algorithm model was kind of devised, and that kind of helped in concluding what is a possible impact source. So this is the structure for FPGA implementation, wherein we take into account location, the data that we collect from two different sensors here, and kind of fit nicely using small number of bits, as you see here, 3 bits, 4 bits, and so on, because we are these all bits are very expensive and to handle, and impact source was kind of identified. So once this is done, yeah, this is a schematic for that. Yeah, so once that is done, the falsification of that is done. Here I'm using CDC for expressing the crack detection and impact source identification. CDC is used for that. So CDC system knowledge base basically is working on three aspects here: falsification, fuzzy inference engine, and defuzzification. And remember, we are trying to fit these all things on FPGA and the VLSI chip, where these chips will be fitting or sitting on our tanks. So this is kind of different numerical data inputs that we take into account. And as a result of that, the fuzzy inference engine will kind of evaluate what is possible, degree of crack, and the source of impact. Degree of crack in the sense, is it like do we have to really take it to degree in the sense, is it like a big, huge crack, or it's kind of something really minuscule which we can easily ignore, and so on. And also the source of impact. What is possible source of impact? So this helps us to gather information about the region in which these vehicles are deployed, and try to make a more informed decision to for further navigation and further movements. Yeah. So I would kind of run quickly through this. Labels, these were the labels that were used, but yes, it depends on what problem we are trying to solve and what terrain. We can kind of change this all information. And same thing, yeah, this was the FPGA and RTL schematic for the CDC implementation, CDC, crack detection and impact source identification. So what I'm trying to kind of portray or bring forward here is that we have a problem to solve. Great, that is wonderful thing, right? More problems, so it's more exciting for us, for engineers, for innovators, for thinkers. They have some food for their brain, they can solve these problems, right? So these problems, they really kind of take into account, or they expect to have some knowledge or some kind of usage of expertise from different fields, like for designing the algorithms and fuzzy models. Yes, great. It would be nice to have computer engineers for setting up the experimentation. Probably metallurgical or mechanical or aerospace engineers would be great to do that, right? And yes, this experimentation and all were done with help of lot of help and input from people with different background and expertise. And finally putting that on the FPGA, and also thinking of having a VLSI chip that can really be fitted on the tanks, on the elements of interest, and run that without human intervention in decentralized fashion. Yeah. So here is kind of a brief background on some of the problems that I have worked in the past, and trying to kind of keep it in such a way that I'm only speaking what I can speak. I don't go into much of details of things and implementation of that. So here we kind of complete the first phase of our discussion on kind of what are different problems that we are kind of handling here. So I'll take a brief pause here, and I'll keep, I mean, you are free to ask any questions or any kind of discussion, or if you want to share something similar. Also, would be great if I can hear some your personal experiences where you have kind of taken into account uh, different, or you have done some truly multidisciplinary kind of problem solved.
Participants, if you have any question or you want to interact, you can mute yourself. Please unmute yourself and ask the questions.
Okay, so great.
Ma'am,
So it means that
maybe
either,
yeah, maybe in last we'll have a question answer session, ma'am.
Hello?
okay, yeah, that sounds good.
Hello?
Yeah.
Ma'am, what was the results for these models you have developed? Any experimental results? What was the?
Okay, so actually, for experimentation, the results were we experimented on different constraints that can be used for the fuzzy node reliabilities and for fuzzy branch reliabilities. And some small models, toy models were used in different settings and kind of experimented on what are the different constraints that we should really take into account and what can be ignored. And for example, if you look here in this case, when we really do this, read the data from the sensors here, we get a lot of information. We have a lot of different data bits. But from that, all different data bits, we kind of experimented and realized that these are the only 4 values that really matter in finding out what can be possibly the whether we have crack or not, and kind of deal with that. So and here in the experimentation, we had used the ceramic plate and used different sources for impact to kind of see what happens with different sources, possible sources, wide sources, different metal or maybe stone or something like that, and see what happens on the crack detection algorithm. And same thing with the impact source algorithm. Yeah.
No,
And
actually,
yeah,
hello?
please go ahead. Yeah, please go ahead.
Question is that have you tried any other models like say hex game models and Euler formula? That which one is better? I wanted to just other than this
Fuzzy model, right?
fuzzy model. Have you tried anything like X game is the one which is for speed and you can obstacles you can cross over and all these things. So
Yeah.
Yeah.
So actually, we had we did give a thought to different models, but then we finally came down. Everything boiled down to the fuzzy model, taking into account the problem that was kind of attempted to be solved. Because here the idea was very clear that we are having these uh, unmanned vehicles moving in very in wilderness where we don't have much of support, and a lot of this information was not very, we cannot have very clear values for those parameters that we take into account. So we thought fuzzy model would be the best model to kind of fit this, and this was done some time back. So I believe that they kind of had plans to experiment with different models too and just check it out, but I was out of that plan.
Okay, fine. Thank you.
Mhm. Okay, great. So if there are no more questions, I believe I kind of conveyed everything very clearly and nicely. Just talking on the, I'm just kidding. Yeah. But or I have kind of made all of you go to sleep and kind of ignore this. Okay. So after all this discussion or some background on a problem that which kind of requires multidisciplinary approach to be solved and tackled, um, I'm moving on to the critical and emerging technologies list. So a lot of areas matter to us, yes, but I thought let us take help of experts. And this is the list of critical and emerging technologies uh, published by the White House, and they publish pretty much every year. And these are the 18 technologies, according to the White House, are of great importance and significance to the national security of United States, according to them. And yes, they also are areas of importance for us researchers, because we are trying to kind of find out problems and we are trying to solve problems, right? And in this day and age, probably a good idea to have a team of have interaction or have collaboration with researchers in different disciplines and kind of work together to solve problems. And in fact, we are blessed to have a lot of problems around us. So we can find out and take a single problem, say, and try to implement that using different technologies as we see here. So I would highly recommend that you take a look at this document and see different areas and sub areas defined for each one of them. For example, advanced computing, we have this different sub areas in advanced computing, which is supercomputing, including AI or edge computing, or advanced modeling and simulation, which was kind of done, data processing and analysis techniques, and so on. So if we go back to the problems that we discussed a little bit, we can kind of map that some of these sub areas were kind of taken into account when solving that problem. For example, yes, advanced, or it was kind of an AI application because soft computing method was used here. Data processing and analysis techniques, yes, a lot of data, used data is kind of generated here when we try to evaluate the reliability of the node or branches, and kind of deciding on what data can be important and what can be ignored. So what is data filtration or data cleaning mechanism, and so on. So it actually is a huge problem. And also the advanced network sensing and signature management, for example, which is mentioned one of the methods, one of the technologies here. Yeah. So kind of sensor processing and data fusion or adaptive optics and so on. So it's kind of amalgamation of different sub areas to solve any single problem that we can think of, or maybe sub areas of AI are machine learning, deep learning, and so on, as you see on the screen here. And different areas. I'm sure these all areas are being discussed in this FDP by different panel of speakers that are being arranged here. And data privacy, security, and cybersecurity technologies, like privacy enhancing technologies, or technology for supply chain security and securing privacy technologies and augmented reality, and so on. And space technologies, like what are different in-space servicing or assembly and manufacturing, as well as enabling technologies, or sensors and data analysis tools for space-based observations and space launch, range, and safety technologies, and so on. And highly automated or autonomous and unscrewed systems and robotics, like on surface or air or maritime and so on. So these are different areas and technologies and sub areas in each one of them. So this seems quite dry and rough, right? Because it just gives you generic list of technologies that are existing and that are of prime importance or significance for a nation's security, say for example. So I went on with another source of source that kind of comes up and shortlists some say top 10, for example, areas of significance or technologies of significance. And I'm wearing a hat of somebody who has worked in academia as well as somebody who has worked closely with industry research. So I thought, let me kind of use a different perspective here and sow some seeds for thoughts for all of us. By no means I claim that I'm expert in these all fields which are highlighted here and which are said to be the areas of prime significance. So what I did is I took up a report from Booz Allen, and Booz Allen every year comes up with top 10 emerging technologies for the Department of Defense and National Security. So they are doing kind of an interesting work. What they try to do is they take into account the critical technology areas proposed by different R&D centers, by different defense labs, by different organizations, agencies that we have around, and they try to kind of study those different areas, and then they try to come up with some top 10 categories of technologies that are of prime importance for a particular year. So they don't kind of just sit and take information from the defense agencies or research and development centers and so on, but they also further go and do kind of venture analysis. What kind of funding has been happening in these different areas? What kind of investment is done by the startup community in the nation? Earlier, if you look into the history of the startups or Silicon Valley, after World War II, basically the defense organizations, they invested and they started and cultivated this community so that they can come up with some great ideas. In fact, if you look at all the great inventions like internet and so on, they have all come, or they were all babies of the research work or product of the research work done by the defense organizations, right? But these days, the community has kind of changed, and the private equity and these companies they have come up with, they move very fast and they have state-of-art research. So what is seen these days is the defense and the private bodies, they work hand in hand. In fact, I was reading an article where the US Air Force was trying to kind of reduce the cost of maintaining the unmanned aerial vehicles or in aerial systems as well as the manned aerial systems. And they realized that probably it is a good idea to kind of take into account the expertise in supply chain management and other fields of the commercial airlines, and try to see what model would be best for us to save cost of maintaining these unmanned aerial systems. So this is just one example. So similarly, the private organizations or the SMEs, they contribute in different manner to the defense ecosystem that we see around us. And hence, the venture analysis kind of is also equally important to understand where the funding is going and what kind of startups are blooming in this day and age. And also the third source was Defense Agency tech watch lists. They have this tech watch list. They kind of come up with the RFPs, and they want certain kind of problems to be solved. So what are they? And the fourth source was their own experts and observations. So I like their method of kind of filtering out what the technology fields or the emerging technological fields, and the subcategories. They had bunch of them, and they filtered out the top 10 emerging using different constraints like market momentum, defense implementation speed, defense impact, technology readiness level, and commercial impact. So here, when we say market momentum, basically based on 5-year investment that is seen around, uh, with help of different sources, the pitch book links and so on, their growth potential and capital investments and so on, and defense implementation speed. So taking into account what possibly will take to implement this in the defense arena, defense impact, how strongly it influences the defense infrastructure and technology readiness level, whether is it hypothetical or it is still in the air, this technology, or it is kind of readily implemented. So different levels of readiness here, and commercial impact. That's how it's going to really make difference on the private sector innovation. So let us try to look at a different technologies here. And these are the top 10 technologies for this year for DoD, Department of Defense and National Security. The names are kind of seen here. We will try to quickly go through each of them and see what the trend is. So I won't kind of talk about each one of them here, but we'll have a slide for each one of them. We'll kind of quickly take a look at them. So here on each of the slides, you would see something called as radar charts, as I'm showing here on the left bottom corner, and we would have investment charts, which is on the right top corner here. So radar charts basically are Pentagon charts, I would say, not exactly Pentagon, but yeah, Pentagon charts with 5 things taken into account: the commercial impact, market momentum, defense implementation speed, defense impact, and TRL, readiness level. Yeah, technology readiness level. And here we are trying to see what was investment done in different sectors. Different colors are for different sectors here, and for different years, whether investment is increasing, decreasing, or what's happening at initial, whether it's IPO or whether it's mergers and acquisitions cost, or private investment in public equity or venture capital and so on. So here, if you look on the radar charts, you'll see green, which indicates high values, and the orangish color is used for low values. This is how you can kind of see the chart here. And here on the radar chart, the reddish is number 1. Number 2 is like as you go out from the center towards the edges of Pentagon. Orange is level 2, yellow is 3, and so on. So here 1 means very immature technology, 2 means it is immature, 3rd means intermediate maturity, 4th is somewhat mature, and 5 is it's very mature. So this is what it means for TRL. So here in TRL, if you have something on the green, it means it's very mature technology, right? And defense impact. How would you rank the impact of these technology to defense sector? So if the impact is sitting somewhere toward the center of the Pentagon, it means it doesn't really impact much. But if it is sitting towards the edge, outside edge, then it has high impact. Same way, implementation speed. So if it is in the number 1, implementation will take about more than 10 years. And if it's on the outskirts, on the green one, outer band, then implementation will take less than 2 years. So that is spectrum of the time that will be taken to implement that. And the commercial impact, the fifth point, or fifth corner of the Pentagon. Here, if it is 1, it means it will not significantly impact a commercial industry. And if you go on the outermost point, on the green, it means it will fundamentally transform or revolutionize or impact virtually every major commercial industry. Yeah. So this is how we can read the radar charts. So for each and every technology, we would have this radar charts sitting here. Oops, sorry. Yeah. So the first one, that is, and a disclosure here, by no means I am expert in these all areas, technologies, but I thought let us try to sow seeds and see what kind of things are happening and what are areas in which people are working these days. Excuse me. Yeah, the first one, that is AI accelerator chips. So here, the aim of these accelerator chips is kind of to speed up AI ML computations, such that the energy consumption is very, very low. And in fact, if you look at the diagram here, on y-axis you see flexibility and the x-axis you see efficiency here. So we are moving from CPU to GPUs and FPGAs, as we saw on the problem of reliability of unmanned ground vehicles, and custom ASIC, which was kind of developed using VLSI design. And we further go into in-memory computing and neuromorphic computing. So yeah, just excuse me for a second. Yeah, I am back. Sorry about this, and pardon me for my voice today. I'm having some cold, little bit of cold. Okay. So here, from GPUs to neuromorphic chips, this is how the trend is moving, and we're trying to move on to that, to kind of advances in silicon photonics have potential to drive the improvements in efficiency of all types of chips that we see here. So on the right top corner here, you would see the radar chart, and here it is clearly seen that this technology is kind of really having high impact on defense as well as commercial implementations and defense implementation. The market momentum is yet to kind of pick up for that. And regarding the readiness level, yeah, we are still there's some time, some path to kind of move forward the TRL here. And the chart for investments trends, that kind of shows almost increase in the investment happening in this area. And on the right bottom, you can see the different fields of applications of this technology. That is computer vision or autonomous vehicles, real-time language processing, kind of near a real-time language processing here, in the sense, say, for example, I'm using some Google Glasses or something like that, and I'm trying to do natural language processing, try to translate a discussion. Maybe some of you can translate what I'm speaking in English in Hindi or Marathi or your local language and try to understand the same thing. So using the large LLM models and so on. So something like that. And also battlefield augmented reality and efficient data centers. So these are different use cases or applications of the AI accelerator chips. And I would highly recommend to each one of you to take a look at this document, because it does talk about the technology, it does talk about strategic insight and the future of this technology. So custom, for example, in this case, custom von Neumann and non-von Neumann application specific circuits like ASICs and photonic data transmission links are kind of something seeing a high amount of innovation, and will definitely, I feel that, have some impact and revolutionize the AI industry the way it is going forward, right? And affecting these different use cases or areas of impact. So the next one is alternative position navigation and timing. So this actually is focusing on the suite of technologies used to supplement, enhance, or even replace the GPS, that global positioning system that we are using these days. And on your left here in the figure, you see that the better timing elements can definitely positively impact mission in both relative and absolute PNT. PNT is used for position navigation and timing here, and systems under GPS denied conditions. So if you look into the first one, which is current SOTA onboard inertial navigation unit, there is such a room of there's a room for errors, because the target is kind of seems very high. The possible signals that move out are in different wide range, right? So if we mix the inertial navigation unit and fusion of both of them, next-gen atomic clocks and LEO satellite signals can help us to pinpoint the target and increase the probability of success of hitting the desired target, something that we see here. And regarding the radar chart here, yeah, the radar chart shows that reasonably good amount of work has been done with respect to commercial impact or TRL or defense impact and defense implementation, but the market momentum has yet to be picked up. And the use cases that we see here are autonomous vehicles, or then underwater or underground vehicles, then spacecraft, commercial vehicles, and GPS denied or contested environments. So if I go back to the application that we were kind of thinking of, yes, this technology would be of great help in implementing reliability of unmanned ground vehicles network, right? And this definitely has some impact on the problem that was attempted to be solved in some way, right? In a very small, minuscule manner. And yes, regarding the different investments, the investment was huge in 2022, I believe, yeah, because of different reasons. You see, different colors on the investment. Here is grays for accelerator, or dark blue is for angel seed, or different elements that are taken into account are private equity, IPO, PIPE, and so on, merger and acquisitions, and so on. So yeah, this is what is the market right now, and number of deals, which is shown on the y-axis too, and number of deals are also kind of quite high here. So this is the next area of our technology that is kind of importance. The third one is autonomous swarms. So autonomous swarms actually is a group of autonomous robots that operate as a cohesive unit to perform a mission inspired by self-organizing, non-hierarchical biological systems. So here, if we again look at the diagram here, it can be centralized, it can be decentralized, which is semi-automatic actually, semi-autonomous, not automatic, and decentralized, which is fully autonomous. So, so this takes back us to the problem that we were trying to solve for reliability of unmanned ground vehicles. So we're trying to just find out one element here, but there are other huge number of things we want to kind of conclude and obtain from this convoy of vehicles, right? Or group of autonomous robots here. So regarding applications of this problem, yeah, we can see applications in agriculture or emergency management. For example, the huge fires that are going on in California right now, LA. So these vehicles can really be of great help to find out what are possible areas of impact and how we can optimize resources to solve or to minimize the impact of fire on in this region. And also in entertainment, I'm sure many of you might have seen this robotic kind of dances or different formations done by robots in the sky. Yeah, something like that. So these are autonomous swarms and methods of drone swarm command and control. Future systems will definitely use semi-autonomous and autonomous decentralized architectures with optimal balance between the two based on specific mission needs, right? In fact, it's kind of amazing to think about the number of drones that are registered. For example, in the US alone, there are about a million drones registered, and out of that, at any point, 8,500 drones are actively moving in the sky for different purposes. So that is kind of the count, and I'm sure the numbers are similarly that big in all different regions in the world. So this is a technology that is of importance, and the radar chart shows that yes, we still have to make a long move in different aspects like commercial, TRL, defense impact, and defense implementation speed. But the market momentum is huge for this. So look at also look at the investment that is seen here on the investment chart on the right hand side here. And on the bottom, you can see different areas of implementation of this technology, right? ISR, weapons, counter swarm, logistics and communication, and so on. So this is the third area of importance or technology kind of that matters for national security. The fourth one is generative AI software development. So here, this technology basically uses generative AI to improve coding efficiencies, which involves code generation, code completion, code documentation, legacy code conversion, and software testing and debugging. In fact, I was, talking to some of my friends, and it was kind of a common observation that people really don't want to sit and do coding now in details. So this kind of tools will be a very kind of supportive or will come very handful to implement software development as a whole kind of thing. And as you see in the diagram here, generative coding tools. So we have training data, desired code function, which is in natural language. You just tell plain English or plain, I'm sure it will eventually come in all regional languages too, and code snippet, maybe some legacy languages there and some testing, proposed testing method and so on. And that generates the code completely. It also does the documentation and does the testing and also has a debug code available. So if you look into the radar chart here, it's kind of interesting to see that there's a huge commercial impact, defense impact, market momentum, and defense implementation right now, as of now. And only TRL is a little bit on lag. So readiness is not yet there, but yes, we are kind of moving in that direction. And look at the investments. Investments are huge in this area of using generative AI for software development. So these are different use cases you see in the black on the right bottom corner for code generation or bug-free code or automatic documentation, code refactoring, code testing, and so on. Yeah. So yes, this is going to disrupt the way software is being developed in coming years. Then the next technology is high density energy storage. And in this, the aim of this technology is to optimize the energy to weight and energy to volume ratios of energy systems. And of course, applications of this includes something that you see on the top bottom, sorry, right bottom section, which is powering drones or automated EV automobile, unmanned vehicles, as we discussed, unmanned aerial systems or unmanned ground systems, and so on, and unmanned water systems, robotics and edge computing and AI. And radar chart also kind of gives us a rough idea of what is the room where we can really contribute and kind of take into account. We can implement or use our energy to solve and kind of work on that. And the investment charts also look great, as you see on the right side here. The next one is technologies hypersonics, technology for testing and production of weapons that achieve hypersonic propulsion. So hypersonic propulsion is something that moves with the speed 5 times the speed of sound, so that fast. So on the diagram that we see here on the screen, we see 3 different kind of moments. The first one is the ballistic missiles moment, which is kind of taking long way. Then intermediate is the hypersonic glide vehicles, and the one that is almost going near the ground is hypersonic cruise missiles. So they kind of move very close to the ground and achieve the speed, best speeds that we can think of. In fact, we also see announcements coming at different government levels, right? They're having hypersonic trains running between Pune and Mumbai so that we can reach Mumbai in just 40 minutes or maybe 24 minutes. That's what I heard. Yeah, that is also kind of coming. So this is the technology where we try to kind of have HGVs. So this HGVs, they travel on parabolic trajectory and glide down towards the target, something like that. So the radar chart also seems there is room for contribution there, right? And same way we see the investment chart. Investment also is seen kind of increasing in this field at different levels. And the use cases or applications can be seen on the bottom right corner for long range strike, commercial transportation, supply chain logistics, and counter strikes, and so on. And the next area is the multimodal AI. So multimodal AI, actually, MMAI is focusing on the models that can ingest or take into account and or output more than one data type. So take into account different types of data to build the model. So this is an example given for a multimodal deepfake detection, as you see on the screen here, and the different modalities that can be used for analysis. So this is an hypothetical model actually, and submodalities such as those listed above must be considered in relation to each other to uncover the signs of synthetic manipulation. So this also is an upcoming area or the technology of prime significance. And we can take a look at the radar chart as well as the investment charts to kind of take a clue or cue on what are the areas that still needs some support and where can we contribute in different areas and so on. And the use cases can be seen on the bottom right. Again, intelligence fusion, human behavior prediction. In fact, was taking at the World Economic Forum, and looking on the social robotics field, social robotic fields, in the sense the robots are kind of introduced in the social places, like say parks or malls and so on, and they are moving like normal human beings, trying to gather information, listen to conversations that are happening around, listen to noises, and try to have some awareness about the situation, and accordingly perform certain set of actions. This is kind of a upcoming field of research wherein these robots are trying to understand human behavior, try to be civilized like humans, try to follow manners of human beings, and make sure, like if they're walking in the mall, they don't come and hit other humans, kind of take care of the norms of civilization in human society. So that is also seen as an upcoming field. Then deepfake detection, predictive maintenance, healthcare diagnosis, and so on. Yeah. So example of healthcare diagnosis is, I had an opportunity to work on the brain tumor contouring project, semi-automatic kind of semi-autonomous hybrid, basically model of brain tumor contouring for brain tumor surgeries. So at Detroit Medical Center, there was this lab where we used to work on taking into account different modalities like CT scan, MRIs, and X-rays, and so on, and kind of finding out the exact location of the brain tumor, because there is a lot of movement that happens in the brain. The tumor won't be sitting at a single location. So taking into account the nature of brain and taking into account these different modalities, it was kind of an attempt to find out the location of the tumor, so that the brain surgeons can kind of figure it out and have minimal offensive surgery done to remove the tumor from the brain. Yeah, so these are different examples of multimodal AI. And yes, if you look at the radar chart here and the investment chart here, they look quite promising. A lot of room where we can actually contribute towards this technology, right? And yeah, so this takes us to the next application or next technology, which is non-kinetic counter UAS, unmanned aerial systems. So it's actually a subset of counter UAS and focused on disabling small, medium-sized drone threats using efforts such as RF jamming, cyber takeover, or directed energy. So HPV, high power microwave, and HEL, high energy laser technology, kind of helps in doing that, to kind of disable small or medium-sized drones. And these are the scopes of HEL and HPM across the region, and kind of design. The ranges, of course, are classified. I mean, we can't really talk about the ranges, but in general, tentatively something approximately we can see the ranges as shown on the diagram here. So AIM is basically to protect the region of interest, right? You may not want any drone coming near, say, for example, places of high significance, our research labs, or some airports, and so on. So we have this technology implemented, which helps us to disable small and medium-sized drones entering into this area of interest. So the radar map here kind of shows there is there's a lot of room for contribution. Market momentum still has to pick up, but otherwise a reasonably good amount of things are done on the other four fronts of commercial and defense impact or implementation of that. So applications, use cases are in swarm, kind of computing, as we saw, or something like mobile air or directed energy hypersonic defense, and crowd protection on our cricket stadiums or for huge programs or huge get-togethers that happen for different festivals or events. So these are different areas or applications wherein we can see the use of non-kinetic US, non-kinetic counter US technology meaningful and useful. And this is the one field. I'm sorry, I don't have that investment diagram put here, but investment is kind of seen quite huge amount of investment seen even in this year to 2024 in this area, and number of deals also are increasing in this area of interest. So that takes us to the next one, which is the ninth technology, the post quantum cryptography. So this technology focuses on math algorithms to secure against attacks by current or future quantum computers. And I'm sure I heard that you had some talks on cryptography and advanced cryptography. So we have to kind of focus on algorithms, mathematical algorithms for public key encryption, which must be defined and implemented today to resist the attacks from quantum computers in the future. And if you look at the radar chart and the investment charts, they look great. A lot of spots where we can kind of contribute. And there's no dearth of applications of these ones, as you see in the use cases towards the bottom. And this is the last one, the space domain awareness technology. And the space domain awareness enables understanding of space operating environment and perceived threats. So it also allows commercial operators to safely fly their crafts, avoiding the debris and maintain the orbital regimes they use. So here, just for your information or a quick kind of understanding, the objects in the space that really have impact are, very small, teeny tiny objects, even of smaller than 1 millimeter. They can damage the active satellites and impact the satellite operations. And the monitoring of active satellites as well as their debris is kind of key in maintaining the situational awareness and safety of the space operating environment. And we see the amount of investment objects which are kind of active and debris on the chart on the left. And yes, we see the radar chart and the investment charts. Great, huge amount of investment happening here, and also huge amount of opportunities to solve problems. So yeah, so these are the cumulative representation of investment happening in different areas that we see around here, and these ones, that is quantum computing, or the investment in non-kinetic counter IAS and so on, or hypersonics or high density energy. Pretty much we see investment increasing in all the fields that or technologies that we see here. And these are the cumulative radar chart for all these technologies that we see here. Yeah. So the whole idea was to bring this together was to kind of give you a glimpse of different technologies that are of significance. And if you take any small problem, you kind of have, you see that might need more than one technologies that you see here, and that impact the solution for that problem. So probably a good idea to have a collaborative environment, a collaborative lab setup to have a team of people working together. Also, as a department or as my research problem, I can focus on some technology and start developing expertise in that one technology on different problems that we see in our day-to-day life. Yeah. So here are the references that are being used. And with this, I would like to thank you for your kind attention. I know it was a little bit monotonous, but I think that is what the way it was expected. Yeah. So I would appreciate any questions or any feedback, comments on these ones. Yeah. Thank you very much.
Thank you, ma'am. Participants, if you have any question, please unmute yourself. Meanwhile, ma'am, there is a question in chat box.
Mhm.
Yeah.
Okay.
Hello.
Yeah. I see that question. Hypersonic train could be possible in India. Yeah. IITM students and professors are testing for longer period, and will it be safe? I would say I would kind of rephrase or refrain from answering the question, because yes, it will be safe. I mean, because a lot of efforts are being done to test it out and check it out. So I'm sure after all that regressive testing that will be implemented actually on the ground, we always have this kind of question when we have new technology or something new that is being implemented.
Hello.
Yeah.
Yes, sir.
Good evening, ma'am.
Yeah. Good evening.
Ma'am, you are talking about the multimodal AI. So, which are the different models that are used in multimodal AI, and which is the more efficient model?
So actually, I don't, by no means I claim that I'm expert in that multimodal AI, but I was trying to kind of just bring into highlight that these are different technologies that can be focused on. I mean, if you are kind of working in this area, I mean, in multimodal AI, then yes, there is a lot of scope for us to kind of move forward, and a lot of problems that can be solved using different multimodal AI models. Yeah.
And ma'am, you are talking about the FPGA. So, can I ask related to that?
Absolutely.
Okay, ma'am, thank you. So, ma'am, when I was doing my MTech project in the cryptography using RSA algorithm, and I would like to simulate that RSA algorithm, and would like to download that simulated program into the FPGA. But what I found that I find very difficult to download that program into that FPGA. So, what precautions or care should be taken while downloading the crypto code into the VLSI or FPGA chip?
So what kind of, may I ask you one question? What kind of
Yeah, ma'am.
difficulties did you face when you try to download them on
Ma'am,
FPGAs?
yes. During that time, whatever the .m file generated by the MATLAB code, that will not be directly dumped into the .bit file. So the conversion should be taken at which place, that I was not aware. So how to do that .m file converted into the .bit file? Now, is it possible nowadays to directly download that .m file into the bit file?
Yeah, actually, I mean, I have worked on this technology a few years back, but I'm sure there are some apps that can help you to convert that .m to .bit files. I was using Synapticad tool for doing that to
Yes,
kind
ma'am.
of convert. I was using the Synapticad for converting the.
No, I was not aware, so I have not used. So I dropped that idea and I made the simplified version of that, and I have work on that version only, because I find very tedious to simulate that FPGA code, and it takes more than 24 hours also. So I dropped that idea and work on some different small RS algorithm type code.
Yeah. So actually, you can use, as I said, some tools. Let me try to bring that slide here. So there are simulators that are available. You don't literally have to kind of do it every time, because if you try to do it every time with small change, you try to go back and try to put that on FPGA, that's going to be very much nightmarish kind of situation. So there are tools that help you to simulate that, like let me try to bring the names of that. Yeah. So Model Sim, yes. Model Sim and Synaptic. So they kind of help to simulate what would happen on the FPGA, and then kind of generate the .bit file finally to put it on the FPGA. Because otherwise, and as you said, at times, depending on the size of code that you're using, it might take hours to kind of put that code on the FPGA and kind of test it out on the FPGA, actual FPGA. So there are simulation tools that really do that for us. So probably that is what we used, and that really helped us. Yeah.
Okay, ma'am. Thank you, ma'am.
Sure.
Participants, any other question, please ask. I think there are no questions. So we come towards the end of our session now. Thank you so much, ma'am, for giving your time and sharing such a wonderful informative session with all of us. I really appreciate that you accepted our request. Once again, thank you so much from Army Institute of Technology. I, Dr. Sita Yadav, co-coordinator of this faculty development program, declared here end of the session. Thank you all. Thank you, participants.
Yeah. Once again, thank you, Dr. Sita Yadavji, and thank you, Dr. Rani, for giving this opportunity. It was nice kind of.
Good night, ma'am.
Good night.